Honeybees are essential partners in our world. They are not just makers of honey, they are vital pollinators for countless flowering plants, including many of the fruits and vegetables we eat every day. Their work supports entire ecosystems and underpins a significant portion of our agriculture. A healthy honeybee colony is a marvel of cooperation and efficiency, a buzzing city where every individual works for the good of the whole. For decades, these incredible insects have faced numerous threats, from habitat loss to pesticide exposure. But among these challenges, one stands out as their most formidable and persistent adversary, a tiny parasite called the Varroa mite. This mite is more than just a pest. It is a honeybee's worst nightmare. Imagine a creature the size of a dinner plate attached to your body, constantly feeding on you. That is the scale of a Varroa mite in relation to a honeybee. This external parasite has become the single greatest threat to managed honeybee colonies worldwide. Its presence is a primary driver behind the alarming annual losses that beekeepers report, with some losing up to half of their colonies each year. These losses are not just a problem for beekeepers. They are a problem for everyone who relies on the critical pollination services that honeybees provide for our food supply. The origin of this crisis lies in a biological mismatch. Varroa mites originally evolved alongside the eastern honeybee, Apis carana, in Asia. Over thousands of years, the eastern honeybee developed natural defenses against the mite, learning to groom them off and disrupt their life cycle. The two species existed in a state of relative balance. However, the problem began when the mite made a host jump to the western honeybee, Apis mellifera. This is the species commonly used for beekeeping in Europe, Africa, and the Americas. Our western honeybees had no evolutionary history with this parasite, and as a result, had no effective defenses prepared for its arrival. This fateful jump set the stage for a global invasion. The mites were first detected in the United States in the late 1980s, and they spread rapidly. Their small size and ability to hitchhike on foraging bees allowed them to move from one colony to another with ease. Beekeepers unknowingly transported infested colonies across the country, accelerating the spread. Within a few short years, the Varroa mite had established itself as a permanent and devastating pest across North America and much of the world. The fight to save the western honeybee from its new and deadly enemy had begun in earnest, a battle that continues to this day. The life of a Varroa mite is perfectly adapted to exploit the honeybee colony. The cycle of infestation begins when an adult female mite, known as a foundress, enters a new hive. She often arrives by hitching a ride on a foraging bee that has drifted from an infested colony nearby. Once inside, her primary goal is to reproduce. To do this, she must find a suitable nursery, a honeycomb cell containing a developing bee larva. The mite is clever. She waits for the precise moment just before the worker bees seal the cell with a wax cap, allowing the larva to pupate into an adult bee. She slips inside, hidden from sight. Once sealed inside the brood cell, the foundress mite begins to feed on the helpless bee pupa. She uses her sharp mouth parts to pierce the pupa's soft body and consume its vital tissues, specifically the fat body. This organ is crucial for the bee's health, acting much like a human liver. After her first meal, the foundress lays her eggs. The first egg she lays is always a male. Subsequent eggs are all females, her daughters. This strategy ensures that her offspring can reproduce within the confines of the sealed cell, a dark and protected environment where the mite family can grow undisturbed. The mite's reproductive cycle is both efficient and sinister. The male mite matures first and then mates with his own sisters inside the cell. The mother and her newly mated daughters continue to feed on the developing bee pupa throughout this time. They weaken their host but are careful not to kill it, as they depend on the bee to eventually emerge from the cell and carry them out into the colony. This parasitic relationship allows the mite population to multiply rapidly, all while hidden away within the very heart of the hive's nursery. Each infested cell becomes a small factory for producing more mites. When the young bee finally matures and chews its way out of the wax-capped cell, it is no longer alone. The original foundress mite and her mated daughters emerge with it, ready to find new hosts. They will climb onto adult bees, feeding on them while they search for other bee larvae to infest. This completes the cycle, turning one infested cell into several. A single mite can quickly lead to a full-blown infestation that spreads exponentially throughout the colony. Without intervention, this relentless cycle will eventually overwhelm and destroy even the strongest and most populous honeybee hive. The direct feeding of Varroa mites is incredibly damaging to individual bees. When a mite sinks its mouthparts into a bee's fat body, it is robbing the bee of essential energy and nutrients. The fat body is a critical organ responsible for immune function, detoxification, and energy storage. When it is damaged, the bee's immune system is severely weakened, making it more susceptible to other illnesses and stressors. This is like a constant drain on the bee's life force, leaving it less able to perform its duties, whether that is foraging for nectar, caring for young, or defending the hive from other threats. Beyond the physical damage of feeding, Varroa mites are also highly effective vectors for deadly viruses. As a mite feeds on one bee and then moves to another, it can transmit a cocktail of pathogens directly into the bee's bloodstream. One of the most common and visible of these is the deformed wing virus. Bees infected with this virus emerge from their cells with shriveled, useless wings, unable to fly. They cannot forage or contribute to the colony, and are soon cast out to die. The combination of a weakened immune system and a direct injection of viruses is a lethal 1-2 punch for the honeybee. Beekeepers must constantly monitor their hives for mite levels to prevent a catastrophe. A common method is the sugar shake test. A beekeeper collects a sample of about 300 bees in a jar, adds powdered sugar, and shakes it gently. The sugar causes the mites to lose their grip, and they fall through a mesh screen where they can be counted. An infestation level of just 2 or 3 mites in the sample, representing about 1% of the bee population, is a serious warning sign. If left untreated, a mite population this size can grow so large that it will cause the entire colony to collapse within a year. Historically, beekeepers have relied on chemical treatments, or miticides, to control Varroa populations. These often come in the form of pesticide-impregnated strips that are placed inside the hive. While these treatments can be effective, they come with significant drawbacks. Over time, Varroa mites have begun to develop resistance to many of the most commonly used chemicals, making them less effective. Furthermore, these pesticides can have unintended negative effects on the bees, and can even contaminate the honey and wax within the hive, forcing beekeepers to search for safer, more sustainable solutions to manage this persistent parasite. As traditional chemical treatments become less reliable, the focus has shifted toward a more sustainable and natural solution, breeding honeybees with their own defenses against the mite. Researchers and beekeepers are working together to identify and selectively breed bees that exhibit mite-resistant behaviors. One of the most successful of these traits is known as Varroa-sensitive hygiene, or VSH. Bees with strong VSH genetics have an incredible ability to sniff out the mites that are hiding and reproducing in the sealed brood cells. They can detect the chemical signals of an infested pupa. Once a VSH bee detects an infested cell, it works with its sisters to uncap the cell and remove the developing pupa. This action interrupts the Varroa mite's reproductive cycle before the mite's offspring can mature and mate. By removing the infested brood, the bees effectively sterilize the foundress mite, preventing her from producing a new generation of parasites. This hygienic behavior is a powerful natural defense mechanism. Beekeepers are actively breeding queens from colonies that show high levels of VSH behavior, helping to spread these valuable genetics to more hives and build a more resilient bee population. Another exciting area of research involves a trait sometimes called mite biting or ankle biting. Researchers have observed that some bees will actively fight back against the mites. These bees will use their mandibles to chew on the mites, often biting off their legs or damaging their bodies enough to kill them. This aggressive grooming behavior is a direct form of defense that can significantly reduce the number of mites on adult bees within the hive. Scientists are using selective breeding programs to promote this trait, raising queens and drones from colonies that are proven mite biters to create stronger, more defensive bee stocks. The future of beekeeping may depend on these innovative breeding efforts. The goal is to create a honeybee population that can manage Varroa mite levels on its own, without the need for constant chemical intervention. This would not only reduce the cost and labor for beekeepers, but also lead to healthier bees and cleaner honey. While we are still far from a perfect solution, the progress in breeding for Varroa resistance offers a powerful ray of hope. By working with the bees' own natural instincts, we can help them fight back against their worst enemy and secure their future, and ours, for generations to come.